Hi everybody, this is lecture 4. This is about Newton's laws of motion. Of course, we've already covered one law of motion, inertia. We'll get to the other two here. Okay, let's get started. So force. We need to review what force is. Remember, the units of force is newtons in the unit system we're working in. It's either a push or a pull. A support force. Let me get an object here. I've got a cup. My hand is supporting the NASA cup. We'll call that a normal force. The force of gravity on the NASA cup, that's the weight. There's external forces acting on an object from the outside. There's internal forces holding an object together. And force is a vector. It has a magnitude and direction. So it can be in many different directions depending on which direction an arrow is facing. Okay, force of gravity and the normal force. We talked about this. Here's a block resting on a surface. The force of gravity is down on the object, pulling it towards the center of the earth. And then the normal force is supporting the block because this platform is in the way. And we call this support force the normal force, and because it's acting normal to the surface. We have this similar situation, but the surface is at an angle. The force of gravity is still down towards the center of the earth on the block, but here the normal force that's supporting the block is at an angle because the surface is at an angle. The surface is at an angle. Okay, so in this case, the block isn't going anywhere. In this case, the block is going to start sliding down. Okay, we talked about net force before. A net force is when you add up all the forces. If there's, if you want to relate what's going to happen to an object and how it's going to move, we need to know what the net force is on something. That means we need to add up all the forces on an object, see what happens. Okay, let's look at these pictures here. So the applied forces, we've got a force of 5 newtons to the right, a second force of 5 newtons to the right. Add them up, we get a net force of 10. This is important. Okay, and this one, we have 5 newtons to the right, 5 newtons to the left. Add those up, we get 0 newtons. Okay, so this is multiple forces over here on the left, but we've got to add them up to get the net force on the right. Okay, what is the net force acting on the box? So 10 newtons to the right, 5 newtons to the left. So net force is going to be, well, there's 10 newtons to the right, 5 newtons to the left. 5 newtons from the left force is going to be canceled by the 5 newtons of the left force. Did I say that right? 5 newtons of the force going right will be canceled by the 5 Newton force going to the left. So overall, that would be a 5 Newton force to the right. So I think that's answer D. Okay, good. And there's the picture. Okay, Newton's first law of motion. Every object continues in a state of rest or uniform speed in a straight line unless acted on by a non-zero net force. Okay, so that's inertia. Inertia is telling us that if the net force on an object is 0, the object will continue to stay at rest or continue moving in a straight line forever until there's a non-zero net force. Okay, the equilibrium rule. If an object maintains its motion, constant speed, constant direction, then the net force is 0. So we can flip it. If we know the net force on an object is 0, then we can say it's going to move at a constant speed or stay at rest. We could flip it and say, if we can see something not accelerating, we can see it at constant velocity through space, or it's at rest, then we know the net force on that object is 0. So for example, if we look at a building, it's not moving, net force 0. We look at a car parked on the side of the street, not moving, net force 0. My NASA cup, resting on my hand, not moving, net force 0. That's the equilibrium rule. Okay, so there's static equilibrium, where the net force is 0 while the object is at rest. There's also dynamic equilibrium, where the net force is 0, but the object is moving at a constant speed in a straight line. Okay, let's check. The equilibrium rule, the sum of the forces equals 0. That's the net force is equal to 0. Applies to vector quantities, scalar quantities, both of the above, none of the above. Since force is a vector, I think it's vector quantities. Okay. A bowling ball is in equilibrium when it is at rest. That's true. Moves steadily in a straight line path. That sounds like equilibrium. So that sounds like both. Okay. And the reason B is in equilibrium is because we said moving at a constant speed in a straight line means the net force is 0. Well, steadily and in a straight line sounds like constant speed and direction. So that means net force is 0. That means it's in equilibrium. Okay, let's move on to Newton's second law. Newton's second law says the acceleration of an object is equal to the net force divided by its mass. Remember, mass is how much matter is in an object. So we can write it like this, that A acceleration equals the net force over the mass, or we could say the force net is equal to the mass times acceleration. Both of these are okay. Okay, let's talk about these: acceleration, force, and mass. If a force is doubled and mass is constant, acceleration is doubled. Okay, so if you want something to accelerate faster, you got to put more force on it. If mass is doubled and acceleration is constant, force is doubled. Okay, so that means if I increase the mass of something, in order to get the same acceleration I had before, got to have a higher force. If both force and mass are doubled, the acceleration is the same. That's right, because if I increase the mass by 2, I got to push harder to have the same acceleration. All of these relationships in these bullet points here are in this equation. Right here, that's what these statements are using, is this equation right here. This is the relationship, these equations are the relationship between force, mass, and acceleration to get these answers here. Okay, let's do some questions. Consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart is somehow decreased to half, the acceleration of the cart, I have to read that again. Consider a cart pushed along a track with a certain force. Okay. If the force remains the same while the mass of the cart is somehow decreased to half, the acceleration of the cart, well, let's look at the equation. So the force is the net force is the same, not changing, but the mass is cut in half. Is that what it said? The mass of the cart decreased by half. So if this is the same and this decreased by half, then the acceleration has to double so that these two things multiplied together give you the same number. So I think the acceleration doubles. Yep. Okay. All right, let's do another question. A certain net force acting on a cart causes the cart to have a certain acceleration along a track. Suppose we push the cart with twice as much net force, but the acceleration remains the same. What is a reasonable explanation? So we doubled the net force, but the acceleration remained the same. That meant mass had to go up as well. So the mass of the cart doubled when the force doubled. That's got to be the answer. The cart experiences a force that didn't before. Well, that's true, but not quite relevant for the question. The track is not level. Okay, that may or may not be true. We're not sure. Friction, reverse direction. Again, we're not sure. That might be happening, but we're not sure. The only one we can say for certain is A. Okay, that's true, A. Okay, friction. Friction again, so air resistance in the previous lecture causing problems. Friction now also causing problems. So air resistance and friction causing problems. They're complicated. Okay, so the idea, resistance to motion. So friction, direction is always opposite the direction of motion. So it's trying to slow stuff down. Okay, there's a couple different types of friction. There's static friction when an object is at rest, and sliding or kinetic friction when an object is in motion. The friction does not depend on speed or contact area. Okay, so whether I increase the area or the contact area, the shape of an object, the friction is always the same. The thing that does change the friction is the normal force that's supporting it from the surface that's feeling friction. We'll talk about that. Recall that it's harder to get an object to start moving from rest than it is to keep an object moving. So I think this is intuitive. So when you're pushing an object, I'll say I'm pushing a box, I have to push it hard to get it going, and then once it's going, I can give it a nice steady push. And this is the difference between static friction and sliding friction. Static friction is often higher than sliding friction. So it's harder to get something moving when overcoming friction than to keep it moving, keep it sliding. Okay, and it occurs between solids and in liquids and gases. So here's an example. We've got a block on a block, the green block on the blue block. If we try to slide these blocks relative to one another, there's going to be friction at the interface because the surfaces grind against one another. Okay, let's do some checks here. When Sanjay pushes a refrigerator across a kitchen floor at a constant speed, the force of friction between the refrigerator and the floor is, well, we see constant speed here. Constant speed means net force is 0, which means the force of friction is exactly opposing Sanjay's push. So one is to the right, and the other is to the left, and they should have the same magnitude. So it's certainly not less than Sanjay's push. That would mean the refrigerator is slowing down, not constant speed. Equal to Sanjay's push, that's true. Equal and opposite to Sanjay's push, thus B is a decent answer, but C is even better because it got the word opposite in there. More than Sanjay's push. So that would mean the refrigerator is accelerating again. So C, I think, is the best answer. Okay, when Sanjay pushes a refrigerator across a kitchen floor at an increasing speed, the amount of friction between the refrigerator and floor is, well, I hear increasing speed thinking net force, not 0. And it sounds like Sanjay's winning the battle against friction because it's increasing in speed. I think that means more, so the friction is less than Sanjay's push. That gives us a net force to the right here. So, if it's equal, then there would be no change in speed. If it was equal and opposite, that's definitely no change in speed. And it's not more than Sanjay's push because that would mean decreasing speed. So it's got to be A. Okay. Okay, let's talk about Newton's third law. Forces always come in pairs. Okay, so here's an example. The pole and the Ferrari have met in a pair. Okay, so if you want to go to the left, which way do you push Y? We'll talk about why the skateboard needs a fan. If it wants to go forward, it's got to push something backwards. Okay, so Newton's third law of motion, colloquially, is for every action or force, there's an equal and opposite reaction, another force. Okay, so let's get some examples here. So if we got this hand, and I think this is a foot, kind of looks like a hand, but it's labeled as foot. Okay, so this foot and this hand are pushing on one another. So the hand feels a force from the foot, and the foot feels a force from the hand. Notice that the forces are equal and opposite and on two different objects. One force is on the hand, one force is on the foot. Okay, if it's a hand in the wall, hand is pushing against the wall, then the hand feels a push from the wall, and the wall feels a push from the hand. Okay. I'm not sure why there's two pictures here. I think this is saying if we can swap the action and reaction forces here. The label is kind of not important. Which one you call the action, which one you call the reaction, they're always equal and opposite and on two different objects. Okay. Oh, it says right there. The answer is it does not matter what you call action and what you call reaction. The two are equal to each other in magnitude and opposite in direction. Okay, and on different objects. That's another important thing. Two different objects. Okay. Object A pushes to the right on object B. Yep, so it's the foot on the ball pushes the ball to the right. What's the reaction force? That's the ball pushing the foot to the left. Okay. A soccer player kicks a ball with a 1,500 newtons of force. The ball exerts a reaction force against the player's foot of... Okay, so we know they're equal and opposite on two different objects. So the player exerts a force on the ball with 1,500 newtons. That means that the ball has to exert 1,500 newtons on the player in the opposite direction. So it's got to be 1,500. Same magnitude. Okay, so let's restate this Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So that's for every action, there's an equal and opposite reaction. Okay, this applies to vehicle accidents. This applies to hammers and nails. Well, everything, anything in the universe. This is true. Okay, Newton's third law of motion. And we're going to connect this to the masses of the objects that are reacting with one another. So I guess this is person A, spherical person A, and spherical person B. If they're pushing on one another, we always know the forces are going to be equal and opposite. If they have the same mass, then they have the same acceleration. Okay, but if person A is much heavier, much more massive than person B, they're going to push on each other with the same force, but B's acceleration will be much more. So if a big person and a small person run into each other, the small person is going to go flying, and the large person won't move much, even though they have the same force on one another. Okay, that's just some questions here. When you step off of a curb, Earth pulls you downward and you pull the Earth upward. Why do you not sense Earth moving upward towards you? Okay, so you feel a force of gravity down from the Earth. That means by Newton's third law, Earth feels a force of gravity from you upward on it. Why doesn't the Earth fall up to you? And the answer is, Earth is falling up to you, but it's so big, its acceleration is so tiny, you can't see it. So why do you not sense Earth moving upward towards you? Earth is fixed, so it cannot move. Well, that's not quite true. It's not fixed, it's free in space. Earth can move, but the other objects on it prevent it from moving. That's not true. It moves, but a very small amount that you cannot see. That sounds like the right answer. Okay. Two people of equal mass on slippery ice push off from each other. Will both move at the same speed in opposite directions. So I see equal mass here. I see slippery, so we're not worrying about friction. Okay, and they push off each other with equal and opposite forces. Since they have the same mass, they're going to have the same acceleration. So yes, and it doesn't matter how they push or the details of the push, doesn't matter. They will move at the same speed. Okay. Okay, so this is a common question. If action and reaction forces are equal, why don't they cancel each other out? How the heck do we get anywhere? So here's an apple pulling an orange. If we look at the orange in isolation, the orange is just getting pulled by the apple. So it's going to have a non-zero net force to the right. It's going to start accelerating and moving. Even though there's equal and opposite forces, because they're on two different objects, we can have motion. Okay, let's see this, the cart and the horse paradox. This is, how can a cart and a horse move if every force has an equal and opposite force? So the key is that the horse is pulling on the cart to the right, and the cart is pulling on the horse to the left. Doesn't that mean that the net force on this whole thing is zero? And the answer is no, it's not. Because let's look at this picture down here. So the cart is pulling on the horse, but the ground is also pushing on the horse because the horse is using its hooves to push on the ground, which is causing a reaction force for the ground to push on the horse, which is then propelling the horse forward, which can overcome this cart on horse force. Okay, so we have to keep in mind this is kind of counterintuitive. It might take some thinking to think about, but even though forces always have an equal and opposite pair somewhere, it's not always going to cancel out. And the reason a horse and cart move is because the horse pushes on the ground, which then causes an equal and opposite force of the ground on the horse, which then propels the horse and the cart forward. Even though the force of horse on cart and force of cart on horse are always equal. Okay, so these are Newton's law of motion that we've done in the past few lectures. We've done Newton's first law, which is inertia. Newton's second law, which is F equals ma, cause and effect. Forces cause accelerations. And Newton's third law, action-reaction. For every force, there's an equal and opposite force. Okay, And here's a Calvin and Hobbes comic book strip. I like Calvin and Hobbes. Okay, let's do some check ourselves questions. Consider a heavy and light person jumping together with the same size parachutes from the same altitude. Who will reach the ground first? Light person, heavy person, both will reach the ground at the same time. Not enough information. Okay, so if it was free fall, the heavy and the light person would reach the ground at the same time. But we have air resistance, and air resistance is caused mostly by the parachutes. And the parachutes they have the same parachutes, same size parachutes. So the air resistance due to the parachutes is coming from the same source, the parachute. Now, in order for the air resistance to cancel out gravity for each person, there must be more air resistance for the heavy person. And to get more air resistance for the heavy person, the parachute and person must move faster to cancel out. So the two people, the heavy parachutist is going to require a higher terminal velocity to cancel out gravity, which means the heavy person is moving at a faster speed, which means the heavy person will get there first. Okay. The force that actually pushes a heavy truck along the road is provided by gravity? Nope. It's not gravity, because gravity is being canceled by the ground. The engine? Sort of, but indirectly. The road pushing on the tires of the truck. That sounds right. The tires push on the ground, and the ground pushes on the tires, which moves the truck forward. If we take the ground away and the wheels just spin, the truck can't move. The air drag acting on the truck, well, that reduces fuel efficiency, but that's not the reason why the truck starts to move. So I think it's C. Okay. And that's it. If you guys have any questions, let me know, and I'll see you for lecture 5.